Now we continue with Professor Giorgio De Pascali from the Politecnico di Torino. He's going to be presenting groundbreaking results from the EU-funded project Mimosa, which isn't about mimosas, although it is midday. We're going to be learning actually about how innovative AM metal composite joints are transforming aerostructures by removing the use of fasteners, improving the efficiency and sustainability, and incorporating circular economic principles, including material recycling. So please take us to the stage. Thank you.
Thank you very much. Right, okay. So this talk is about one of the applications of additive manufacturing from metal materials to aeronautics. And in particular, we talk about joints between metal parts and composite parts. I am from Politecnico of Torino, that is a university in Italy, one of the main universities. I led this laboratory that is called Smart Structures and Systems, where we work on research about innovative structures, innovative processes and materials, and multifunctional devices. There is a link to the website of the laboratory, so you are invited to visit the website and to check our projects in case you are interested in some similar activities. This project is focused on multi-component structures, as you know, in many fields like aerospace, automotive, energy generation. You have the combination of different materials, in particular composites and metals. The requirements for these fields are, of course, the low mass, but also the free form. So you must be able to shape your component as you prefer. And so there are some consolidated processes to do this and to join these materials. And up to now, the most used strategies to join the materials are strategies based on mechanical devices, so like bolts, or by adhesives. These are both good strategies, but they have some limitations, especially related to the processing time, the number of steps of production involved in this joining activities, and also about the footprint of these processes. So we decided to introduce some innovation in this activity, starting from the aeronautic field, with the goal to have a reduced mass, because when you use rivets to join these parts, you introduce weight, because the rivet, of course, introduces weight. And on average, on an aircraft, you have about 100 kilograms of rivets only. That is a lot. And we are trying to remove this additional weight. Of course, by removing the rivets, you can also preserve the integrity of the structure, because you avoid to drill holes. That means stress concentration. So it also increases the lifetime of the component. And of course, design for recycling, because we need to reuse the materials. And an additional needing is to reduce the environmental footprint by lightweighting the structures. That means less fuel consumption, and also to reduce the energy for the process itself. So according to these new needings, and according to the standard that today in the aeronautic field includes 13 steps to build metal composite joints, we proposed a new solution made only by 5 steps. That has a huge impact on the business model, on the economic impact of the development in terms of time, energy, and cost. The strategy is based on an interlocked joint, where the metal part is shaped with some functionalized surface with small anchors, which are able to engage the fibers of the composite without rivets and without glue. Of course, we need to optimize a lot of things before to have a reliable joint, but with this strategy, it's possible to have a really strong impact on the final sustainability of the process. And so we built a consortium of 7 companies to provide the technological development and to develop a prototype of this joint. And so we applied for funding from the European Commission, and we create the Mimosa project. That is a 3 years long project. I am the coordinator of this consortium that is composed by 7 companies and 2 research centers, where the end user is Leonardo, that is the main Italian manufacturer of aircrafts. And we have also the TÜV Süd company for the qualification and standardization of this new process. The project started 2 years ago. We are at 2/3 of the project now. The final goal is to develop a prototype of a vertical stabilizer of a passenger aircraft, where we have 6 fittings like this that couple the vertical stabilizer to the fuselage. Today, these fittings are connected with rivets. Our project will remove the rivets and will add this functionalized surface to that. Of course, there are many things to do in the project. Today, I will speak briefly about the design and the additive manufacturing process behind this. But we have also a lot of work, especially about recycling of materials, because one of the goals is to reuse materials to provide a cyclic economy, circular economy of this technology. So we provide the recycling of metal by atomization of metal parts after service to generate new powder for new additive manufacturing processes. And also recycling of composite by pelleting the scraps. Another big part is the certification, because when we use special processes like additive manufacturing in aeronautics sector, we need to qualify almost everything from the material to the machine, to the process, to the final component. And sometimes it's very difficult, and sometimes we need to write some new guidelines to do that because they are not written in the standards up to now. So this is these are 2 big parts. We started from some patents that today are owned by Polytechnic of Torino and that will be disclosed with the final users. Just a few words about our activities as designers. We started from a lot of simulations of the fluidic force, fluidic interactions with the structures to calculate, of course, the external loads acting on our joints, with the goal to calculate the forces acting on the joints to properly dimension the joints. So we made a lot of FEM simulations that are very complicated because, for example, in this part, we have 306 different elements combined together with 7 materials. And so it's a huge work of simulation to get the final reactions and forces on the joints. From the first prototypes, we can see the result of what we are doing. So we are getting some special shapes of these anchors in the metal part. The metal in this case is the aluminum alloy that is currently used in additive manufacturing, and the composite part. So we are able to join the 2 materials by optimizing different steps of the 2 processes to avoid vacuums, to avoid failure of fibers, and so on. But as you can see in this way, the load can be transferred from the fiber to the metal parts without any additional element, external element, and without glue. Another big part is the simulation of what happens at the interface, because we have the combination of metal, epoxy matrix, and carbon fiber. That means a lot of complicated interfaces with different materials and different theories behind the transfer of the forces. I don't go into details, but for example, the different organization of the layout or the layup of the layers changes a lot the final behavior of the joint. So this is one of the parameters of the optimization. And of course, in the micro scale, we also have to calculate each single strand of fibers, which effects produce on the joint and on the force transfer, and we get some maps of stress and strain distribution on a single anchor that will be multiplied per the surface to the surface of the joint to get the final force. Of course, depending to the shape we get to this, we assign to this anchor, we have different behaviors. And so the shape will be optimized depending to the load direction that you have on the joint. And additive manufacturing is very good for that because it allows a big freedom in defining shapes, of course. Here, for example, are some simulations of the force transfer when we apply a certain load on a certain sample, and so on. Here, there are some additional tests to optimize the additive manufacturing process where you need, as you know, to get the best volume energy density by setting the laser power, the laser speed, the layer thickness, and so on. And when you have the combination of bulk materials and thin structures, this is very challenging because you have to tune the properties when you switch from the bulk part to the thin part. And so this is the best optimized compromise we got. Another point is the joint, is the notch between these parts, because in the notch you can have stress concentration, and this must be reduced, and so on. Of course, we tried different setup, different shapes of anchors to get different results. Okay, just to say something more about the additive manufacturing process, that is the main topic of this event. Here you can see the timeline of our project. In particular, I will focus on the post-process treatment, where we have a heat treatment of the metal part, and the autoclave curing of the composite. Why I want to put the attention on this? Because this curing in an autoclave will have an influence on the thermal treatment on the metal. And so we'll modify the properties of the metal that you have optimized with, for example, the T6 standard curve. So there is an alteration of the mechanical and of the microstructural properties of the alloy. This is an innovative problem because normally we print a part in metal, we apply heat treatment, and the part is released. But here it's not the same because we need to apply another thermal cycle. And so what happens is something like this, where we have a temperature profile over the time. This is the standard part, so stress relieving, solution annealing, and aging. But after that, we need to cure the composite. And so the practical effect is that we have an extension of the aging of the metal as well. What is the effect of this? The effect of this is that when we move from the as-built situation to the standard T6 curve, and we apply on the standard T6 curve the autoclave curing, you can see that the stress, maximum stress of the material reduces. So the mechanical properties of the material are degraded. So it's not a good consequence for the design of the component. So what we have to do is to change the standard T6 profile to include also the autoclave curing with a sort of iteration of processes, because depending to the size of the component, this part changes. And so you must optimize the two things together. That is not easy. Then just to give you a fast view on the tests, that are a lot of tests we did, is the optimization of Young modulus of the material with the relative error. You can see a lot of bars here. Each bar is an average of 5-6 samples to get some consistent results. The yield strength also of the material. You can see that by changing the heat treatment, this property changes a lot. And we need to optimize both Young modulus and yield stress. That are two competitive properties. It's not possible to maximize both together at the same time. When you increase one, the other one decreases. So you have to compensate these two situations. And finally, the density. That, of course, is really important. Okay, just a few pictures about the samples to show you the experimental campaign behind this work that is very huge and is supported by our partners that are working specifically on additive manufacturing and also powder recycling. Here there is some videos. This is one of the first prototypes of one fitting. You can see here is one of the 6 fittings that are joining together the fuselage with the vertical stabilizer of the aircraft. In this solution, we have the surface covered with 3D anchors that will serve as a connection to the fibers, the composite fibers. Here you can see just the powder removal from the machine and the release of the part. Of course, we have to optimize something like the shape, the size, the orientation of these anchors that are defined according to the directions of these forces. Because if the force changes direction, you can optimize in a different way this orientation, and so on. And finally, here there is another movie about the coupling of composite parts and the metal part. This is a demonstrator. We put just half of the surface to show the adhesion and the properties, the mechanical properties that we have tested, and they provide values that are even higher than the equivalent joint do with traditional rivets. So we are very happy about this result. The next steps that already started are about the fatigue test of this component, because you know that when you apply cyclic load, things may change because you have crack initiation and crack propagation at the interface. And so we are testing this part at now. And also, the notch effect associated to this. The next step is to build and assemble the prototype together with Leonardo Aerostructures that will serve for demonstration of the technology from one side, and also for the validation of the external loads, because we will apply functional loads on this prototype to measure the effective strength of the joint. We had some events in Italy to show these important results. We had a meeting in May at the National Automobile Museum in Torino, where we had 120 attendees from enterprises and stakeholders, and also the president of Piemonte region attended to the conference, and with a press conference, of course. So we are starting to disclose this innovation to create an environment of industrial partners to exploit these results. The same thing has been done in June at the European Commission in Brussels, where we meet the same kind of companies from all the European countries, also with the same goal to disclose the technology and to involve new partners in this development. And the same thing is today, the same goal is today. So I try to involve other people interested in these technologies to share their competencies, to give suggestions to improve our results. Some thanks to my some of my collaborators that are from Politecnico, from companies. I just mentioned few people that are directly linked to this presentation, but the group is composed by more than 30 people and 40 people. And so there is a lot of work behind this. These are my contacts, so feel free to visit the website of the project, to write to me at this email. And I'm open to new cooperations. We are open to new solutions to solve new problems for different applications with this technology, or even with some similar investigation. So thank you very much for your attention. If you have questions now or later, I'm free. So please ask. Thank you.
Thank you very much, Giorgio. So
yeah.
Is the Mimosa project closed now to new participants, or are you looking for new participants for that project or for new projects?
The Mimosa project is still running for 1 year, so we are open to exploit this technology with end users that may work in different fields, not exclusively on aerospace, but for example, automotive, racing, energy generation, and so on, by transferring this technology. One of the goals of the European project is to share the knowledge, to transfer the knowledge to the other people by receiving new requirements for new products and share the competence. So it's not a closed know-how.
Okay.
Of course, we have some restrictions for this application with the companies involved here, but the technology is open. So we are open with other companies, to other companies. Okay.
Perfect. Thank you very much.
Thank you. Thank you.
Thank you.